you?
My name is Gabriel, and today we're here to present UCI CubeSAT II.
So what's a CubeSat? A CubeSat is a miniature satellite that is used for space research using cheap components, usually built yourself to do it as cheap as possible. One unit CubeSat is a 1 meter cube, and it can weigh as much as 1.33 kilograms. And it all started in 1999 in Cal Poly, and they did all the specifications for the CubeSats. So if 1 unit is 1 liter and 133 kilos, 2 units, it's going to be 2 liters, 2.66 kilograms. And we have to meet the specifications if we want to use one of the launch opportunities provided periodically. Our objective is to design and build a 2 units satellite in order to measure and control the pollution clouds that are around the world, mainly in the most populated regions, such as India and China. And we also are going to test a new prototype of electrospray thrusters, and we are also going to use the thermal radiator that the spacecraft thermal team are developing. So the new design of the electrospray thrusters, it's a new design developed in Manuel Romero's lab, and basically the main difference is that the thrust provided by the electrospray is controlled by the acceleration voltage applied instead of the pressure gradient between the tank and the outside medium. And this allows us to have a non-pressurized tank, also less components, which makes the whole system lighter and with less volume.
Another innovation of our project is the air pollution study. Currently, there are only a few satellites in space that are looking at the ozone or trying to track any movement of weather. Two of the ones that I looked at is the ozone mapping and the profiler suit. These 2 satellites went in 2011, and the other one was roughly 2008, and they both only look at the ozone, and that's like as close as any satellite is looking when it comes to clouds or any type of weather climate. The other 2 are also ozone monitoring and mapping, which also their project was to just look at the weather, see how the global warming is affecting us, and other types of arrangements with ocean and the speed, since a lot of people are trying to get energy out of the ocean now as a renewable source. So for us, this innovation is pretty good because it hasn't been tested or used. So there's a lot of funding that we can find and is going to be used for the next year when it comes to like solar tracking and weather cloud patterns as well. For the next year, we want to create a new iteration of the 2U CubeSat. The current design is off of the NASA website, and they allow students to use it. The purpose of that was to allow us to understand FEA controls, since I was the first student to take FEA in the winter, and that took all quarter for me to understand and actually get. So also we want to do design and testing of the electrospray thrusters, which Leah is going to talk more about.
Yeah, basically we've built and tested the prototype in the vacuum chamber already, but we were using a capillarity tube made of silicon carbide, and the tip of the meter of the electrospray needs to be conductive. So we were using, we were coating it with platinum, but some kind of chemical reaction is happening, so the coating is going away. So now we are going to use platinum needles instead, and we are currently about to test this new prototype with platinum needles. And we also need to test everything. Once the final design is done, we need to test all the thrusters to check its stability and repeatability, because they need to be very reliable if we want to use it as main control system.
Another goal that we have for the future is to finish and build the power units and the circuits. Currently, I have one electrical engineer that's willing to come onto the team for next year. He has another friend that's going to help us with the communications. As far as the power that we've gotten from this year, we've only been able to understand how much we need and what kind of circuits we're going to use. Having these 2 new members joining in is going to help us a lot, because that's going to give us the actual circuitry and the actual communications aspect of the satellite. Next slide, please. So currently our budget was relatively expensive because we were looking at space grade things or components, and when we talked to Gamero, he said that most of our components should be off the shelf, meaning that we should be able to get them through a really reliable source and really cheap. And from there we can actually make them test ourselves and see if we can actually put them on the satellite and make them space grade ourselves. So with that, just by looking at components on the web from different CubeSat shops, our budget would come out to roughly $5,000, which is really expensive. And for a launch provider, the minimum price that we found was $8,000, and that would be piggybacking being roughly the third being deployed out of the rocket. Right now, we only have $1,000 for our budget, and that came out just from units itself. For the future, for next year, we're going to apply for Europe so we can actually get more funding. And then we're also going to look through other companies that are willing to fund this project, because no one out there is actually looking for the cloud movement and seeing how that affects pollution and where it's affecting most of the people. So for the team that we have currently, we have Gamera as our advisor and Leah as our graduate advisor. I'm the project manager, and these are the only team members we have currently. So this year, we completed the 2U final element analysis with the final decision of aluminum 6066. We've actually done the frequency testing, and it's going to pass based on the specifications given on the NASA website. For the solar panel design, we chose gallium arsenide as our solar cells, and we're going to get them from Spectral Labs. Currently, we are in a funding dilemma, so we are not going to be able to get all the solar cells we need for the CubeSat. For the circuit board, we have our members working on it. They created a rough sketch of what the circuit's going to look like in PCB. Leah's going to talk about the thrusters.
So we established the needed testing procedures in order to test electrospray thrusters. As I said, we need to know that they are stable and reliable. And we also test the first prototype, but we saw that after 10 hours or so it starts failing because the coding starts going out. So we are going to test the new prototype.
We have chosen our camera and our camera chip, and it is going to pass pixel regulation, which is a topic that came up last quarter. And I looked on the regulations, and it is going to be able to pass all the regulations when it comes to the camera and the lens specifications. For future work, we want to fabricate the 2U unit. We also want to do iterations of the 2U. Cal Poly has started their own frame as well, so we're going to try to go into that mentality of creating our own. So I have assigned the new structures team of creating a new iteration of the current design, just so that it's a UCI CubeSat within itself. For the solar panel design, we're going to build these solar panels in-house. So we have to get all the solar panels and test them to see the reliability. And we want to test how much current we can get out of them and how much voltage we can get when they're in parallel or in series.
For the electrospray thrusters, as I said, we're going to test a new prototype, and we are going also to design and test the distribution mechanism. Basically, it's because we only have one tank inside the spacecraft, and we need at least 6 thrusters, or maybe 7 if we want main propulsion. So we need from one capillarity tube, we need 7, and since we don't have pressure gradients, we need to design it such the liquid can break into these 7 capillarity tubes. And well, it depends on capillarity forces, and we have to check if it works.
As in concerns for the camera, we have to purchase and test the camera to make sure we get the pixelization we want, and just to see how much voltage and current is going to require and how much heat is going to come out of that, and what temperatures it needs to operate once you actually plug it into the rest of our system. For the future work, we also want to create a power subsystem. As I said, I have an electrical engineer coming in next year, so he's going to help a lot with that. He's actually emphasizing or specializing in circuit design. The other engineer we're going to get is communications. He specializes in bandwidth and understanding the frequencies in which satellites communicate. He's going to follow all the regulations and create a design aspect out of this. And the last thing we're going to work for the future is the actual ADCs, which is the attitude determination and control system, which controls our satellite once it's deployed into space, making sure we're always pointing towards the Earth and that the solar panels are always getting the maximum incidence angle to give us the maximum power output we need. So this quarter, we learned a lot of lessons. For the first quarter, we were basically trying to grade a goal, understanding what our satellite was going to test, what was going to happen, and our team decided to do this because it is very innovative and it's going to impact the world a lot. Another thing we want to change is that each system has to have a Gantt chart. In the this entire year, we had one Gantt chart for a whole team, and we want to create a Gantt chart for each subsystem so that each lead has power over his members. We want weekly summaries and blogs to be gathered by the team lead versus just being turned into the team project manager. Currently, everyone is just submitting their written report, their PowerPoint into the file, and the team lead doesn't assess what's actually going on with his entire members. For the specification sheets, we found a lot of information from NASA and Cal Poly and the FAA, which these are going to now dictate the design iterations that we're actually completing versus just Googling and trying to see what we're going to do for the future. Most of the research we're going to depend on is FAA and NASA, since they have been publishing a lot of works on CubeSats. And then lastly, we're going to use and abuse the CubeSat room, since we didn't have access to it because the previous project managers didn't obtain the keys, and none of us knew that the room was actually available for us as long as we wanted. For future, we want to use this Gantt chart. The Gantt chart is very important because it helps us with down selection and design iterations, and it also helps us with cost and budget analysis. For organization, we want to use Trello because this is going to be like a design thing where you have a use, work in progress, to do, and done. And this clearly states to the members what needs to be done, what's going to be done, and what has to be done. Also, we are trying to look for committed members. Right now, this year, we only had 4 to 5 members every quarter, and these members only took 1 unit, and that's equivalent to 4 hours a week. And if you have a project that's going on for a year with 4 hours a week, not much can actually get done. So we're trying to include next year is a unit limit, which is 2 units, which is 8 hours a week, and as long as they come into the CubeSat room, I'm pretty sure they can get their 8 hours done pretty quickly, and they'll be more motivated to actually be part of the project versus just trying to do their work at home and not be as motivated as possible. That is our project.